Hello, in this video we'll be talking about yet another way of solving systems of linear equations using matrices, this time using the matrix inverse. Let's begin. So to remind ourselves where we've been, we have definitely taken a lot of time setting up and solving systems of linear equations with matrices. Remember Gaussian elimination, where we had to get REF form? Remember Cramer's rule, using determinants? Well, today we learn another way of doing this, called using a matrix equation and the matrix inverse. So first of all, let me tell you what I mean by a matrix equation. In our last video, we talked about matrix equations, right? We solved for matrix X, but we really didn't have any context for why that was helpful. This time what we're going to do is we're actually going to see how we can set up any system of equations using the matrix AX equals B. All right, so let's take a look at our slide here and we'll see that matrix pop up. At the very top of that slide, do you see it? It says AX equals B. What am I talking about? Well, matrix A is our coefficient matrix. By coefficient matrix, I mean a matrix which only has the coefficients of my variables from the system. So for example, let's do this in context. Take a look at the system of equations in the middle of your notes on this slide. We have x minus 7y equals 3 and 2x plus 3y equals 23. So if I were to ask you, what are your coefficients, you would say, well, the coefficients of x are 1 and 2. And the coefficients of y are -7 and 3. So when I say the coefficient matrix A, that's the matrix I'm talking about. Notice here it's a 2 by 2 matrix because it has only 2 columns, an x coefficient column and a y coefficient column. So if it helps you to put a little x and y on top to keep things straight, feel free. So notice that was a 2 by 2 coefficient matrix in this example. Next, we're going to define matrix X. Matrix X, I'll use maybe red here, see if we can differentiate. A little different, okay. For matrix X, the variable matrix, we notice that in the system here, the matrix equation here, we have A times X. And in the last video, you can go back if you need to watch it, when we introduced matrix multiplication. We said that the only way we could multiply two matrices together was if they had the same inner order. Good job. So notice here that matrix A has 2 columns, which means if I'm going to multiply it by matrix X on the right, it would have to have 2 rows. So in this case, if I have 2 rows, but there's only 2 variables possible, it must be a 2 by 1 matrix with entries of x and little y. So this is what we mean by matrix X, the variable matrix. It's size 2 by 1 in this case. Now remember, again, from last video, we talked about once you've multiplied the two together, the size should be the same as your outer order. So let's take a look at the outer order here. That's right, 2 by 1. And that's what matrix B, the resulting matrix of the product, should be. No pun intended. So matrix B should have 2 rows and 1 column. Well, that makes sense because matrix B is known as our constant matrix. Okay, so what I'm claiming here, what I'm proposing, is anytime you have a system of linear equations, another way of solving that system, besides all the methods we've done so far, is to rewrite the system as a matrix equation. But not just any matrix equation. It has to be this variety. A times X equals B. You'll have to memorize that and practice it until you really understand why that is. Matrix A was your coefficient matrix, matrix X was your variable matrix, and matrix B is your constant matrix. What I would recommend for you is to actually take time, pause the video, and multiply this out. If you take row 1 of A times column 1 of X, you should set it equal to the entry 3. And you'll end up getting the first equation of your system. And do the same thing for the other entry, and you'll get the second equation for your system. Very important for you to understand, this is not made up. This actually does model your system. Okay, once you believe me there, then we're going to have to solve that equation, aren't we? Now, we talked last video about how to solve a matrix equation for matrix X, but the last example we did in that video only had to undo matrix addition with matrix subtraction, right? But I mentioned there is no such thing as matrix division. So how would I undo this matrix product, A times X? That's a great question. Now, if you've ever taken trigonometry or you plan to take it maybe next semester, or maybe you're even taking it right now, A lot of students do that. You'll learn about the inverse of like the sine wave. So you'll be trying to solve an equation like, let me write it up here, like sine x is equal to 1/2. Maybe that's ringing a bell or you're totally confused right now. One of those is possible, okay? Turns out that the only way to solve that equation was to use sine inverse on the left. That was able to undo the sine and give you just x equals sine inverse of 1/2, and then that would be your 30 degrees or pi over 6 if you know anything about trig, okay? Now, that's one example of inverses. An easier example of inverses from your early arithmetic days are if someone told you, I would like to undo matrix multiplication, right? So if you had, for example, 3x equals 6, you could undo numerical multiplication by using the inverse of 3, which is 1 over 3. It turns out that's your inverse of 3, the multiplicative inverse, in fact. It's called the reciprocal. So you've dealt with inverses before, or you're going to be dealing with them a lot more if you haven't done trigonometry yet. But I bring all of that up because I'm about to make another bold claim. And the bold claim I make is that you can solve this matrix equation for x by simply multiplying both sides of that equation by something called A inverse. It's written a to the -1 power, but that is read A inverse. So it turns out when you do that, that A inverse times A, just like 1/3 times 3 would give you 1, the identity of multiplication for numbers. You'll get something called I, which is the identity matrix with 1s along the diagonal from left to right and 0s everywhere else. We'll be studying that some more in the coming slides. Okay, it turns out if you multiply any square matrix, so n by n, same number of rows as columns, by matrix I, you get back to the same matrix. It's like multiplying a number by 1. You get back to itself. So why do I say that? Because now you would have I times x, which leads you to just x, and that's what we wanted. So here is what you're going to be doing. You're going to be using something called A inverse, multiplying it by b, and you'll get the answer, the variable matrix x. It's a very nice way of solving a system. But I'm assuming that I can find A inverse, and we're going to learn how to do that at the end of this video by hand. But for now, there's a link in your notes that will take you to a YouTube video that will show you how you can find A inverse in your calculator. So feel free to use technology at this point until we learn how to do it by hand. So assuming you found A inverse by going into technology and asking it to give you the inverse, let's suppose that they give us our inverse, and it is the 2 by 2 matrix, with row 1 being 3/17, 7/17, and row 2 being -2/17 and 1/17. So nasty fractions, okay. It turns out if we understand that this system of equations is really the same as ax equals b, then we can solve for x by multiplying this A inverse, which we have using technology, or we're given it in this case, times matrix B. So this was A inverse times matrix B. Now last time we learned how to do this. We learned how to multiply these two matrices, and you're welcome to use technology or do it by hand. In this case, I would have a 2 by 2 times a 2 by 1. So what size should the product be? That's right, 2 by 1. 2 rows, 1 column. It turns out when you do this, if you multiply 3/17 times 3 and 7/17 times 23, you'll end up getting a big number over a smaller number, and when you reduce it, you should get a 10 here, okay? And similarly, when you do -2/17 times 3 plus 1/17 times 23 and reduce, you'll end up getting the number 1. And what does that mean? Well, that's telling us this is matrix X, which was our variable matrix, with entries little x and little y in that column. So what do we know now? Well, we have our solution set. We now know that these two lines are intersecting in space when x takes on the value 10 and y takes on the output of 1. Okay? So that's the one and only time where these two lines are intersecting. Now, right now, I totally understand if you feel like that was a waste of time and you'd rather do this using substitution or elimination. I feel you. However, when you get bigger and bigger systems, this will be one of the fastest ways of solving that system of linear equations, as long as you have technology, because it'll save you a lot of time. Okay, so let's take a look on our next slide at how we could find A inverse by hand and how we could practice using it. So in this case, we're still telling you, use technology, go ahead and find A inverse. I've even provided it for you in case you have trouble with that video right now, if you just want to work along with me. So here we're told to use inverse matrices along with technology to solve the system of 3 equations, 3 unknowns, where equation 1 is 9x plus 7y plus 4z equals 12. Equation 2 is 6x plus 5y plus 4z equals 5. And equation 3, 4x plus 3y plus z equals 7. Okay, so if we're asked to use a matrix inverse, that must mean that we're talking about matrix equation AX equals B, because that's the only time an inverse pops up. This is where we know that X must equal A inverse times B. So if we know this fact, we're going to be in great shape. Okay, so what do we need to do? Well, we need to define our terms, right? What is matrix A in this case? Well, remember that's your coefficient matrix. So in this case, that would be the 3 by 3 matrix where the X coefficients for the first column are 9, 6, 4. The Y coefficients for the second column are 7, 5, 3. And the Z coefficients for the third column are 4, 4, 1. So that's defined to be matrix A, a nice 3 by 3 matrix. And then we're talking about matrix X. I'll get another color, maybe red here. Here we go. So matrix X is defined to be the variable matrix. So the variable matrix has to have 3 rows, that's right, and 1 column it looks like, because there's only 3 variables, little x, little y, and little z. And finally, they're supposed to equal, when I multiply them together, what matrix? B, that's right, the constant matrix. So matrix B must be what size according to what we know about matrix multiplication? That's right, 3 by 1. So 3 rows, 1 column, with entries which are constants of 12, 5, and 7. Okay, so what does this mean? Once we defined our terms, we are now able to use technology, could do it by hand, but this would be a lot faster with technology, to find X. So matrix X should equal A inverse times B. Well, using technology, you could find A inverse yourself by simply typing in the entries for matrix X and then hitting the inverse button. This would pop up. Row 1 is 7, negative 5, negative 8. So 7, negative 5, negative 8. Row 2 of A inverse is negative 10, 7, 12. Negative 10, 7, 12. And row 3 of A inverse was 2, negative 1, negative 3. Now, I usually, when I'm in a face-to-face class with students, they usually raise their hand at this point and say, Professor, where did you get A inverse? And I would show them using technology where I got A inverse from. But in a few moments, if you're really wondering, how could I do this by hand? Don't worry, we're going to do it. But I first wanted you to see the uses of it, okay? So there is A inverse, and we're going to learn how to do it soon by hand. And we're going to multiply it by B, which was 12, 5, and 7. So we have a 3 by 3 times a 3 by 1, which is possible because they have the same inner order. And what will our result be? Well, feel free to pause the video and practice your multiplication skills from our last video and see if you get the right answer. Okay, so when you did your multiplication to get this first entry, there's 3 entries here for the 3 entries of the column, you would have done your first row with your first column. So 7 times 12, negative 5 times 5, negative 8 times 7, add those products together, and you should have ended up with a result there of 3. And then for your next entry, did you get negative 1? And then for your last entry, did you get negative 2? If you did, good job. What is that saying? Well, again, that's X, where matrix X was your variable matrix, little x, little y, little z, right? So that must be telling you that your solution set is the ordered triple when X is 3, when Y is negative 1, and when Z is negative 2. So there's only one place in space where those 3 planes are coming together. It's at that location. Okay. Again, technology is much faster than doing this by hand, but if you want the practice in your homework, feel free to make yourself do it by hand, okay? At this point, let's transition to finding the inverse by hand. So let's get over to our next slide and do that. So what do we mean by finding the inverse by hand? Well, first of all, there's only certain types of matrices that even have an inverse. Just like when you learn trigonometry or when you will study trigonometry, there's only certain types of one-to-one functions that have an inverse, right? So similarly, there's only certain types of matrices that are invertible, having inverses. And the first definition or requirement is that your matrix is square. So you have to have an n by n matrix to begin with. Same number of rows and columns. If you put it into a calculator and you said, calculator, find the inverse of this 2 by 3 matrix, it would say, error, invalid dimensions. And that's because it must be a square matrix. So we'll start off with an easy 2 by 2 matrix, and then we'll work our way up to a 3 by 3 matrix. But the technique that we'll show works for any n by n matrix which has an inverse. So let's take a look in context here of what we're asking you to do. Suppose we have a 2 by 2 matrix. So 2 rows, 2 columns, where the first row of matrix A is 4, 3, and the second row of matrix A is 1, 0. Well, to find A inverse, you have our step-by-step approach above. Take a look at it and pause the video if you like. What we're saying is that to find A inverse by hand, the way that will always work, there are shortcuts for smaller ones like this, but the way that will always work is to form what we call an augmented matrix, where A is on the left. Now, we've done that before. It might sound familiar to you when we did Gaussian elimination, where we were trying to get REF form with 1s on the diagonal and the 0s below. We would have put the matrix on the left, and then we would augment it with the constant matrix. Similarly, we begin by putting matrix A on the left. So we have our 4, 3, 1, 0 on the left side of the matrix. I usually put a little line there to indicate that I've augmented it. And on the right, we're going to put the identity matrix. I mentioned that in a previous slide today, but remember what that was. This identity matrix was the matrix which is the same size as the actual matrix you're starting with, so 2 by 2 in this case, where there are 1s along the diagonal and 0s everywhere else, including up here. Okay, so it's not just like your REF form, it's like RREF in a sense, except for a square situation. So again, what does an identity matrix do? Well, it means that if you were to multiply your matrix A by the identity matrix, you better get back to the original matrix A. And in fact, I would encourage you to pause this video and check for yourself that this is true. If you were to multiply matrix A, which is 4, 3, 1, 0, by matrix I, which would be 1, 0, 0, 1, do you in fact get back to matrix A? That's the question. So I would really encourage you all to pause the video to check that out so that this becomes really reality and not just a rule that someone made up and told you about. Okay. So at this point, that's what the identity matrix does, but here's how we're going to use it. Okay. We're going to form our augmented matrix with A on the left, so here is A, and on the right, we're going to put our identity matrix. I'll use maybe sky blue. Here we go. The identity matrix is on the right there. Okay. So you build this ginormous augmented matrix. If you thought your homework for Gaussian elimination was hard, this is going to be even more tedious, I promise. So I don't like to sugarcoat it. It's going to be time-consuming by hand. But again, you can always use technology in real life and to check your answers in your homework. So let's take a look at how we would do this. Do you remember back when we did Gaussian elimination that we could do certain row operations in order to get the 1s on the diagonal and the 0s below? Exactly. Same thing here. Step 2 in the instructions above to find A inverse by hand tell us that we're going to be performing row operations until we have transformed the matrix so that there are 1s on the diagonal and 0s below on the left side. So what we want, our goal, I'll write it up here for you. Our goal is to start with A on the left, I on the right, and after row operations, it might take 3, 4, 8, it might be a lot, to end up with I on the left, and whatever is on the right will be A inverse. Okay, so we're going to get started here. Let's remember what our row operations are. For row operations, we could either, put them down here, we could either switch rows. You can go back to our earlier video to remember row operations. We could multiply rows by a number. Some students mistake multiplication with multiplying a row by another row. Can't do that, but you can multiply a row by a number as long as it's not 0. And the third one, if you can see it, I'll put it over here maybe, was that you could add multiples of rows together. So those are our basic row operations that we used back in the day for Gaussian elimination. Multiples of rows. Okay. So with that in mind, let's begin. We take a look at where we start and talk about where we'd like to go. Right now we have a 4 in that top left corner, but we would like it to be a 1 in order for it to truly transform into the identity matrix on the left. So an easy way to do that would just be to switch rows, wouldn't it? Yeah, let's do that. Let's switch rows 1 and 2, and the way we wrote that was R1, double arrow, R2. So the new row 1 would become the old row 2. 1, 0, 0, 1. The new row 2 would be the old row 1. 4, 3, 1, and 0. Okay, so we have one entry correct. There's a lot more to go, I promise. Okay, so we have one entry correct. Next up, we would like to go right below it and transform that entry, which is currently a 4, into a 0. That's right. So to make it a 0, we could multiply a row by a number and add it to another row, which is what we're doing right here. So if we try to multiply, maybe multiply row 1 by maybe -4, would that be okay? And add it to row 2, putting the result in row 2. Let's see what that would produce for us. I'm going to copy and paste row 1 because we haven't changed it. 1, 0, 0, 1. But the new row 2 would be, you can pause and do it yourself if you like. That's right, -4 times 1 is -4, plus 4 is 0. That's what we wanted. 0 times -4 is 0, plus 3 is 3. So that changed. 0 times -4 is 0, plus 1. That's 1. And 1 times -4 is -4 plus 0. That's going to be -4, isn't it? So this is our new matrix at this point. Well, we've gotten very, very close now. There is only one problem. That's right. This 3 in entry 2-2 should be a 1. So how could I make that happen? What could I do here? Well, I could multiply a row by a number, couldn't I? I don't always use all of the row operations, but I think it's fun that in this case we did, didn't we? I could multiply row 2 by the reciprocal of 3, which is 1/3. So if I took 1/3 times row 2 and put the result into row 2 right here, let's see what that would produce. Well, the old row 1, we'll just copy, was 1, 0, 0, 1. And the new row 2 will be 1/3 times each of those entries. So that would be 0, that would be 1, 1/3, and -4/3. If that's what you got, great job. If you made a mistake somewhere, make a note of where you made that mistake. As humans, we typically make the same mistakes over and over again. So it's really important to find where we're making those mistakes and then try to correct them. So let's see what this is telling us. Big picture here. So in the big picture here, what we've discovered is that once we have this being I, this time we didn't even have to work too hard because it just so happened that we had a 0 in entry 1, 2 in the first row, second column. It was already there for us. But sometimes you'll have to do an extra step to make that happen. But by getting I on the left, according to this definition, we should now notice that whatever is on the right must be A inverse if we did everything correctly, if we didn't make any mistakes. So A inverse should be row 1 of 0, 1 and row 2 of 1/3 and -4/3. Lots of ways to check this. If you have technology, you could have just asked your calculator to find A inverse, couldn't you? Type in A, hit the inverse button. But if this was a situation where you didn't have that type of technology and you wanted to test if this is truly the inverse, here's how you would have to check it. The purpose of an inverse is that it undoes multiplication, leaving you back to the identity, which is the identity matrix. So you would check it by saying, when I take A and multiply it by A inverse, do I in fact get the identity matrix? If you don't, you made a mistake somewhere. Okay. So this is really important that you can understand the process, but also understand how to check if you made a mistake or if you got it right. Okay, so we have, I believe, one more example. It's a little bit bigger, so make sure that you understand this one first before you go on to the next one. And I would really recommend you pause it, try it yourself, and then check out your answers with me. So in example 2, we're given A as a 3x3 matrix with rows 1, 2, 3, 2, 3, 0, and 0, 1, 2. We are asked to find A inverse by hand. And again, because we're given numerical entries, you could definitely use technology as a good way to check this, or if you were using it to do it by hand, not do it by hand at all. But since they're asking for us to do it by hand, let's go through the process. So again, feel free to try it yourself and then come back to me. So what do we do first? If we're finding A inverse by hand, you should always have a game plan. Figure out what they're asking for and how to do it. Right? To find A inverse by hand, where do we begin? That's right. We start with an augmented matrix A on the left and I on the right. And what do we do then? That's right. We do row operations. This time I think usually it takes at least 7 operations for this one. So we're going to do row operations until we get I on the left and A inverse on the right. Now, the way I'm about to do it is my personal choice, right? We have those 3 row operations, switching rows, multiplying rows by a non-zero constant, and adding multiples of rows together to replace other rows. But you might take a different path than me, and that's perfectly fine, as long as you've used valid row operations. Feel free to do it a different way than me. So I begin by noticing that when I make this A here on the left, 1, 2, 3, 2, 3, 0, 0, 1, 2, and I on the right, 1, 0, 0, 0, 1, 0, 0, 0, 1, I already have something that I'm after, noting that I already have a 1 in entry 1, 1 in the top left corner, which is what I want if I'm trying to get 1s on the diagonal and 0s everywhere else for the left side of this matrix. So that's good news. But I also noticed something really interesting. If I were to switch a couple rows, I would get 2 other entries exactly where I want them. Do you see which row I'm thinking of switching? That's right, rows 2 and 3. Again, you may not have seen that. Totally okay to go about it a different way as long as it's valid row operation. So if I had switched rows 2 and 3, look what would have happened. Well, first of all, I could copy and paste row 1. So row 1 is unchanged. It's still 1, 2, 3, 1, 0, 0. But if I switch rows 2 and 3, look what we get. 0, 1, 2, 0, 0, 1, and then the new row 3 would be the old row 2, 2, 3, 0, 0, 1, 0. Okay, does anyone see out there why I did that? That's exactly why. You got it. It is because I noticed that now I would get my 1s on the diagonal for the first 2 rows, and I would get a 0 below that first 1. So that's excellent, because what we are after, again, is 1s on the diagonal and 0s everywhere else, including above the diagonal this time, because it truly has to be the identity matrix. Once we have that, whatever is on this side is A inverse. So that is the goal. Okay, so here's where we are. We now have a situation where in row 3, column 1, we have a 2. But what would we like that 2 to become? Can you think about what should that 2 become? That's right, that 2 needs to become a 0. So I can't multiply by 0. Remember, that's not allowed. You can only multiply by non-zero constants, even though it's tempting. Okay, so what could I do then? Well, I could switch rows, but that's not going to help me either. How about adding multiples of rows together? Could I do that? Yeah, I could multiply row 1 by something. That's right, by -2. So if I multiplied in this step row 1 by a -2 and added that, actually I could make it easier on myself. Let's just do it a little bit easier on myself. So the signs could be either way, but I'm going to try to think ahead, think wisely, right? Work smart, not hard. So if I actually thought a little smarter here, instead of multiplying by a -2, couldn't I just multiply by +2, row 1, and then subtract row 2? Row 3, putting the result in row 3. Let's see what that would produce then. And I'll come on down here so you can have some space there. Try not to cut off my head here. Here we go. Yeah, we're still good. Okay. So let's take a look at what our new row 3 would be. Well, first I'll copy and paste rows 1 and 2 since they're unchanged from the step before. So 1, 2, 3, and 1, 0, 0 is still row 1. And 0, 1, 2, 0, 0, 1 is still row 2. But let's get our new row 3. By doubling the entries of row 1 and subtracting row 3 from it, we should get our new row 3. So 2 times 1 is 2, minus 2 is 0, so that was the 0 we were hoping for. And then we're going to go to our next one. 2 times 2 is 4, and 4 minus 3 is 1. Interesting. Next up we have 2 times 3, which is 6. And 6 minus 0 is, that's right, 6. Okay, next we have 2 times 1, which is 2, minus 0, which is 2. 2 times 0 is 0, minus 1 would give me a, that's right, -1. And 2 times 0 is 0, and 0 minus 0 is, kind of boring, but 0. Okay, so here's what we have now. Let's take a look, survey the damage and the success. We have ones on the diagonal here and here. We have zeros below the first one in the first column. And we also notice that we have something very interesting. In row 3, we have a 1 in entry 3, 2, and a 6 in entry 3, 3. So at this next step, what are we after? What are we trying to do here? Let's get another color going on. That's right. We would like for this 1 to turn into a 0. That's right. Well, this isn't too bad. And again, you could either subtract row 2 minus row 3 or row 3 minus row 2 and make that your new row 3. I think I looked ahead and it looked like the signs are easier for us if we do row 3 minus row 2, but you could do either one. Either one is perfectly acceptable. So if I did row 3 minus row 2, putting the result into row 3, let's see where we'd be. This is a tedious one, I warned you. Here we go. I'm copying and pasting rows 1 and 2. Make sure I don't make any mistakes, and if you see one, you're always welcome to email me and let me know where I made a mistake, and I'll let the class know. And then we have 0, 1, 2, 0, 0, 1 for row 2. Okay, so for our new row 3, let's do it carefully. We're supposed to take row 3 minus row 2 and put the result of that new row in row 3. Here we go. This would mean 0 minus 0, which is 0. That's good news. We don't want to change the good stuff that we already got. We worked hard for. Then we would do 1 minus 1 and get 0. That was what we were after. Good news. 6 minus 2, because we did row 3 minus row 2, is positive 4. 2 minus 0 is positive 2. Negative 1 minus 0 is still negative 1. But 0 minus 1 will change this entry to a negative 1, won't it? Okay? So we're getting closer. Now, the bad news is we're not one step away. We're still several steps away. And the reason is this is not a situation where we have a 3x4 augmented system and we just need REF form and back substitute to get our answers. That's not what we're doing. Remember the goal. We are finding, I'll go over here again, we're finding A inverse, which means we need to have the entire identity matrix on the left, meaning I must get zeros above as well. Okay, so let's talk about our next step. Where are we at? Well, we have the ones in the diagonal for rows 1 and 2, the zeros below all of those ones, which is excellent news. But next up, we would like for entry 3, 3, third row, third column, to change from a 4 into a 1. You got that right. So what could I do here? That's right, I can multiply by the reciprocal of 4, which is 1 over 4. So if I did that, 1 over 4 times row 3, and that will become my new row 3 here. Let's see what we get. I'll copy and paste rows 1 and 2. 1, 2, 3, 1, 0, 0. Then for row 2, 0, 1, 2, 0, 0, 1. And let's get our new row 3. 1/4 times this row would give me 0 and 0 and 1. That's the good news. We were hoping for that, right? The collateral damage is really important still because that's giving us A inverse eventually. So let's take a look. When I do 1/4 times 2, I get 2/4, which is really 1/2. Good news, that's the right answer so far. So if you had checked in your calculator, you're like, oh, that's looking okay. All right, good. How about 1/4 times negative 1? Well, that's negative 1/4, or negative 0.25. And finally, 1/4 times negative 1 again gives you the same result, negative 1 over 4. Okay, so we have actually the final row of A inverse because that row is not going to change anymore. The 0, 0, 1 is identical to what we wanted here in the identity matrix. So that part is good. We're done with that part. We have 2 more rows to worry about. Namely, if you look ahead, above rather, we would like for, in row 1, column 2, we would like for that entry, instead of a 2, we would like for it to be a 0. And also in row 2, column 3, we would like for this entry 2 to also be a 0. Now it is possible to kill 2 birds with 1 stone, or I think they say feed 2 birds with 1 stone, whatever you say. You can do 2 things at once is what I'm trying to say. And what I mean by that is you don't have to write down a matrix twice here. You can actually do 1 matrix for both of those steps. Save you some writing, I hope. You're welcome. So what would this look like? Well, let's think about it. If we want to make the first row, second column, change from a 2 into a 0, what would I need to do? That's right, I would need to multiply row 2. Let's see if you can see me if I write over here. Yeah, you can see me. Multiply row 2 by, let's see, what did I choose here? Row 2 by negative 2. and add that to row 1, putting the result into row 1. Similarly, if I wanted to get entry 2, 3, so in the second row, third column, if I'd like to change that 2 into a 0, what would I need to do? That's right, I would need to multiply the row 3 below also by -2 and add that to row 2 to get my new row 2. Notice I'm not touching row 4. Sorry, row 3. There is no row 4. I'm not touching row 3. I'm simply copying and pasting that one. So let me do that copy and paste job. 0, 0, 1, 1/2, -1/4, and -1/4. We are almost done, I promise. I know this has been a long problem. Okay, let's see where we're at. When I do that, I get -2 times 0 plus 1. Well, that's just 1. Good, we didn't want to change that. -2 times 1 is -2 plus the 2 above it. That's the 0 I was after. Yay! -2 times 2, I'm looking at the row 2 from the previous matrix, that would have been -4. Adding -4 to 3 is -1. That's actually quite nice. You're welcome. Then we get to our next part of the matrix in row 1. We would have -2 times 0 from row 2. That's 0. And 0 plus 1 is still 1. So that's unchanged. We would have -2 times 0 in row 2. Well, that's 0. Plus the 0 above it is still 0. And we would have -2 times 1 in row 2. That's -2. Plus the 0 above it, that is -2. So hopefully I didn't make a mistake there. I went kind of quickly. We'll find out. Here we go. So let's go to our next row operation. We're doing -2 times row 3. We're adding it to row 2 and putting the result in row 2. That would mean -2 times 0, which is 0, plus 0, which is still 0. That's good news. We didn't change what we had worked for. Similarly, below it, we're not changing at all for the next one either because 0 times -2 is still 0, and adding 0 to 1 is still 1. Finally, here's the entry we're looking for. -2 times 1 is -2 plus 2 above it. That's the 0 we were after. So that was the goal here. Finally, let's get our collateral damage. We're going to be done with row 2 here. Here we go. -2 times row 3. Well, that would be -2 times 1/2. Well, that's just -2/2, which is -1. If you add that to the entry above it, you have -1 there, which is the right entry if I were looking at my calculator. So far, so good. Okay. Let's take a look at the next entry. -2 times -1/4 is +2/4 or 1/2. Adding that to the entry above it, we would get +1/2, which again is correct if you're checking with technology. And finally, for the next entry, -2 times -1/4 is still 2/4 or 1/2, and adding 1/2 to 1 is really 2/2 plus 1/2, which is 3/2, also known as 1.5 if you prefer decimals. So if you check with technology, you'll see that that row is completely right. We have row 3 for the inverse and row 2 for the inverse. So I know I'm done with that because I have 0, 1, 0, which is the second row of the identity matrix. We only have one more step, thank goodness. Here we go. Here's our last step. Get ready for it. Last step, we would like for entry in row 1, column 3, which is currently a -1, to become a, that's right, it needs to be a 0. So to make it a 0, what do we need to do? It's very nice this time. What do we do? That's right, we can add rows together. So I'm going to add which rows? That's right, row 1 with row 3, putting the result into row 1. Notice you can just copy and paste rows 2 and 3. They're unchanged here. So I'll do that briefly. Copy and paste. Wish that was an option. Here we'd have 0, 1, 0, -1/2. Sorry, I already made a mistake. Let me make some more space so I don't rush it. Here we go. Do that one again. And get my pen. Here we go. Okay. So I'm in row 2. I had done 0, 1, 0, and then I'd have on the other side of the line -1/2 and 3/2. We're not changing that. And in row 3, we already had 0, 0, 1, and on the right side of the line, we have 1/2, -1/4, and -1/4. So I'm just copying and pasting, hopefully correctly. It's really easy to copy a sign wrong. Okay, let's do our last step finally. When we add rows 1 and 3 together, the goal was to get a 0 in entry 1, 3. Let's see if that happens. Well, we would take 0 plus 1, that's still 1. 0 plus 0, that's still 0. 1 plus -1, that's the 0 we were craving. So there is my identity matrix, finally. Okay. Again, technology is much faster than doing this by hand. Okay. And finally, for the last row on the right side, we would continue. We would add up rows 1 and 3. We'd get 1/2 plus 1, which is really 3/2. We would get -1/4 plus 0, which is -1/4, -1/4. And -2 minus 1/4 is -9/4. So it turns out, on the right, we found a inverse. Now, it is so easy to make an arithmetic error or a copy error, so you would definitely want to be checking with technology whenever you have a matrix given to you that has numerical entries like we did here. Okay. Again, if you didn't have technology and you had to do this by hand and you had to check it, remember what you need to do to know you're right. Not just to check yourself step by step, but you'd have to check, if I take A, which I was given, times A inverse, I should end up with what? That's right, the identity matrix. If I don't end up with the identity matrix, one's on the diagonal and zero's everywhere else, I don't have the inverse, do I? Okay, and what do inverses do? They help us to undo matrix multiplication so we can solve equations like we did earlier today, AX equals B. All right, that was a lot. So if you're exhausted, take a break. Don't do this when you're tired. You will make mistakes. But once you have a fresh set of eyes, get back to your notes and plug away and see if you can do at least 3 in a row correctly to become a master of this stuff. I'll see you next time. And remember, math is not a spectator sport, so get to work after you rest.